All right. So, if you haven't already looked at the study guide for this test, do that. It'll tell you everything that you are expected to know for this test. It's sections 2 and 3. So, like I said, there's a lot on this test. It's get a little tricky. There's a lot of mechanisms, a lot of reactions. But the individual ones aren't that hard. It's just a lot. So, it goes all the way back to aromatic compounds. And one of the first things we talked about was Huckel's rule. So aromaticity is basically just a special stability that aromatic compounds have because of a conjugated pi bond, which means that you have an alternating single-double bond in some kind of ring. And basically, so all of these carbons have an unhybridized p orbital above and below. So above and below. And they all have that, and they could basically all share those pi electrons from the double bonds all around the ring. So they all spread out, and that makes it more stable because the higher volume or area a charge can spread out to, the more stable it'll be.
So if he asks, like, why are aromatic compounds unusually stable, we can say that, but, like, would another valid answer be because of the alternating double bonds that create all the carbons are tertiary, but, like, in a normal cyclohexane, they're all secondary? Can we say that and it'd be right, or?
No.
Crap.
So these are not tertiary, right? Because they're still only connected to 2 carbons.
Darn. Never mind. Yep.
Does that make sense?
Okay,
So
it's because of the conjugated pi bond system.
yes, you'll need to know that word.
Conjugated pi bond system.
Yeah. So if he does ask that, the correct answer would be something to the effect of the conjugated pi bond allows the pi electrons to delocalize throughout the entire ring, which lowers energy, stabilizes the ring. So if he would ask why aromatic compounds are more stable, it would be because of the conjugated pi bond.
It allows the electrons to be localized.
Mm-hmm. Yeah, it allows the pi electrons to delocalize to the entire ring. Okay, so how do you tell if something is aromatic? Use Huckel's rule, which is if the number of pi electrons fit into the formula 4n plus 2, where n is a whole number, then it's aromatic. So in the case of benzene here, and to count pi electrons, you can either count how many carbons there are. So there's 6 carbons, 6 pi electrons. Each carbon contributes 1 pi electron. Or you can count the double bonds. So there's 3 double bonds. Each one has 2. So that's 6 pi electrons. So if I put 4n plus 2 equal to 6, 4n equal to 4, n is equal to 1. So because n is a whole number, this is aromatic.
So wait, so the 4n equals inside?
Hmm?
So I thought the 4n makes it aromatic, and then 4n plus 2 makes it anti-aromatic.
No, so if 4n plus 2 equal to the amount of pi electrons, if n is equal to a whole number, that is aromatic. 4n equal to pi electrons. If it's equal to 4n, that is anti-aromatic.
I didn't get that just now.
I thought it was the other way around.
I did too, yeah.
Really?
Yeah.
I mean, it's an easy phase.
Yeah, no matter.
As long as you, like, equal 4n plus 2 to a number and it comes out whole, it's aromatic.
Yeah, and you will be asked to do that.
But if it, like, 1/2.
Yeah, so if it's like 1/2, it's 1/4, blah, 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 something to that effect. Anything but a whole number. Okay, any questions there? We good? No, we're not good, or no, we don't have?
No, we don't have
Straight roll.
questions.
Okay. Okay, EAS reaction. So this is like nitration, halogenation, alkylation. And the basis of these reactions, because aromatic compounds have that conjugated pi bond, they're electron rich. They can donate those pi electrons to something else. So they're nucleophiles. And nucleophiles, they can react with electrophiles. Those are EAS reactions. Okay, so I just went ahead and wrote down this mechanism to save some time, but if we need to go back and do it together, we can. So you only need to know the nitration and halogenation mechanism. Alkylation, we'll get there later. But, so the net reaction, you react an aromatic compound with nitric acid in the presence of sulfuric acid or another acid. You end up with nitrobenzene and water. And you do need a catalyst for this, or it won't happen. So to have this reaction happen, you need an electrophile. This is not electrophilic by itself. We need to make an electrophile. This is still nitric acid, right? So it's HNO3. So I'm going to protonate it with another acid. I'm going to protonate this OH group. And I didn't show the mechanism. You don't really need to. He doesn't normally do it, but you can if you want. So you're going to protonate this OH group, which is going to make water, which makes this bond break. That can come off. So you'll end up with this cation and water.
So you said we don't have to show the top line?
No, you don't have to show, like, you do need to show this,
Oh, okay.
but you don't have to show,
Oh,
like
okay.
where you get to this part and then that bond breaks, or
Okay.
the other way. You don't have to show that part. You can if you want to, but he normally doesn't. He normally just shows it just like that. But you do need to show that part.
There he is.
Hello. Okay. So now I have a positive charge. Now this is an electrophile. Now that it can react with the ring. So the electrons will come from one of these double bonds, go to the nitrogen, okay, which will break this double bond. So the nitro group will add to one of those doubly bonded carbons. Double bond will break. So then on the other carbon, that'll put a positive charge because we're missing a bond now. Follow that? Because all these carbons have one hydrogen, right? So they're just not shown. So if I add this onto one of them, this is the hydrogen that was already there. There's one hydrogen here, but when I take away that double bond, this only gives us 3 bonds. So now it's positive charge. And this is benzenium. And this is just a class of carbocation. Okay. So I add my nitric group to the ring, and then we need to get rid of this positive charge. So this CH bond is going to break. These bonding electrons will go to reform the double bond, which will get rid of that positive charge. So I end up with nitrobenzene, and then this hydrogen came off and reformed my catalyst. Make sense? Any questions? Okay. So halogenation, this is the other EAS mechanism you need to know. So my net reaction, you react aromatic compound with a halogen in the presence of this catalyst. This is aluminum bromide, but you can also use aluminum chloride if this is chloride, so on and so forth. This is a Lewis acid. So my net reaction, I'll add one of the bromines to the ring and then end up with HBr as a byproduct. And you also need a catalyst for this one. So similar to the last one, this is not an electrophile by itself. I need to make an electrophile before it will react with the ring. So this is my bromine here. One of these lone pairs of electrons on bromine is going to attack the aluminum on my catalyst and form an aluminum bromine bond here. we're just going to put a positive charge on this bromine because it wants one bond. I just gave it an extra one, so it's not happy. That's a positive charge. And that puts a negative charge on this aluminum. Okay. So now this Br-Br bond is going to break, and this bromine is going to also connect to this aluminum here, which is going to give me this ionic compound here. And this is what I want, because I want a positive charge on that bromine, so it's an electrophile, so I can add it to the ring, right? Okay. So now that I have this positive charge, now I can react with the ring. So same thing, the air should come from one of these double bonds to the electrophile, which is the bromine. Okay. I'll break that double bond, add the bromine to one of those double bonded carbons, which is going to put a positive charge on the other one. And then same thing, the CH bond is going to break, and those bonding electrons will go to reform that double bond, get rid of the positive charge. So I end up with bromobenzene, and then this hydrogen is going to bond with one of these bromines on this anion to form HBr, and then that will give me my catalyst back. All good? Okay. So alkylation, like I said, we won't do the mechanism for this just yet. I can't remember if this is later this semester or next semester.
So it's the home test now.
The reaction is on the test, the mechanism is not. But you will be asked to finish, like, he would maybe give you like this part and ask you to finish the reaction. So you will need to know the reaction and the products it gives, but you don't need to know the mechanism. But it's very similar to halogenation. Okay, so alkylation, we're going to react an aromatic compound with an alkyl halide. So this could be chlorine, bromine, iodine. And you're going to have the same catalyst from halogenation. So whatever this is, this will match it. So this is aluminum chloride. And then my net reaction, I'm going to replace one of the hydrogens on the ring with this, with the alkyl group, and then that hydrogen is going to bond with the chlorine. So generally, we'll have RX. R is an alkyl group, X is a halogen. Okay, so that's your general reaction to your alkyl halide catalyst with the alkyl group on the ring, hydrogen from the ring bonds with the halogen. All good? Okay, so on to section 3, which is your functional groups. We started with alcohols. And alcohols, when you react an alcohol with an alkali metal, so sodium, lithium, those are the only ones you'll really see. Can do with the other ones, but those are the only ones you'll really be given. You'll form an alkoxide. So what happens is you'll replace that hydrogen on the OH group with the alkali metal, which will give you a negative charge on your oxygen, positive charge on your alkali metal, and then give you just your hydrogen by itself. But because hydrogen can't be by itself, you write it as half of H2, just in a balanced equation. 1/2 of H2. So just one hydrogen. It's the same thing here. Here, just replace the hydrogen with whatever alkali metal you have. Now we'll put a negative charge on the oxygen, positive charge on the metal, and then hydrogen. Okay, and these are alkoxides, which are going to be important later because alcohols are weak nucleophiles, right?
Yes.
But when I put a full negative charge on that oxygen, I'm going to make a strong electrophile. So that's going to be important later. Okay. So, dehydration of alcohols. This is one of the mechanisms that you'll need to know. So in net reaction, I have to catalyze with acid and also heat. So in net reactions, I'll take that OH group off along with one of the hydrogens on the adjacent carbon, form a double bond, and water. So dehydration, you're taking water off, right? Okay, so the mechanism, I want that OH group off, right, but it's not a good leaving group, so it won't come off easily, so I need to protonate it to make it a good leaving group before I can take it off. So the lone pair of electrons on oxygen is going to take hydrogen. I'm going to make water, which can come off. So because I took that water off, now I have a carbocation. And be careful on these reactions because when you have a secondary or tertiary alcohol, you can form a carbocation. But when it's a primary alcohol, you cannot form that primary carbocation, right? Because it's too unstable. So if you do have a primary alcohol, instead of forming a carbocation in that step, it'll just all happen in one step. The water will come off, and you also take the hydrogen and make the double bond all in one step. But there's an example of that in the PowerPoint and classes. So just be careful and pay attention to the alcohol you have. Okay, so this is a secondary carbocation. And now this CH bond is going to break. The bonding electrons will go to form a double bond, which will neutralize that positive charge. Which gives me my product and my catalyst back.
Are we allowed to just put like H plus even though it's H, like catalyst is actually H2, but it's in the mechanism?
Yes.
The H plus?
Yeah.
Okay.
So it's the hydrogen is what's actually catalyzing the reaction. So and he switches back and forth sometimes, but you can also use the whole sulfuric acid molecule if you want. And then
there's something in the notes where you just like the whole thing.
yeah, so then you would end up with that anion, which you would show taking that hydrogen, but to reform sulfuric acid. But I think it's easier like this. It's up to you though.
And he won't care if you do it.
I'm like 99% sure. I would maybe triple check with him, but
Okay.
and if he did, I would vouch for you and tell you that it was okay. I seriously doubt it, but I would triple check.
Okay.
Just before you do. because the proton is really what's catalyzing it. I think the only time he really does that is with the primary alcohols, because he shows the anion taking the hydrogen at the same time the water leaves. That's the only time I think he uses the whole molecule. By the way, you should be good with. Okay, all good? Okay, Lucas reaction. This is also one of the mechanisms you'll need to know. So, your net reaction, you'll replace that OH with whatever halogen you have and form water. Byproduct, and this will happen without a catalyst. This mechanism is kind of similar to dehydration. Starts out the same way at least. So I want that OH group off, right? I can't take it off there because it's not a good leaving group. So I'm going to protonate it, but I'm going to protonate it from this HX, whatever halogen I have. Okay, so lone pair of electrons from oxygen will take that hydrogen, which will break this bond. Okay, so that forms water here, positive charge on the oxygen, so now I can take this off. And I'll also form this anion here. So I'll form a carbocation, and then this anion, it's a nucleophile, right? So it'll just attack that positively charged carbon to form a carbon-iodine bond. And that's my product. Any questions there? That one's one of the easier ones. Okay, so phenols. Phenols are a class of compound that's an aromatic compound with a OH group on it. Be careful here because these are not alcohols. They do not do alcohol things. They will not react with things like alcohols do. So because of this conjugated pi bond system, right, with all the unhybridized p orbitals sharing all of these pi electrons. So oxygen has 2 lone pairs of electrons, right? So because I have this big mess of pi electrons, these electrons on oxygen can also jump in this whole mess and delocalize to this ring too. So if I'm pulling electrons away from this oxygen, that's going to weaken this OH bond, right? So that makes phenols weakly acidic. So when you dissolve a phenol in water, some of it partially dissociates. So I make alkoxides by reacting alcohol with an alkaline metal. I make phenoxides, which are similar, but I make phenoxides by reacting a phenol with a strong base. So I can have an acid-base reaction. This is an acid, this is a base. So I'll make a salt, ionic compound, and water. Okay, so the important thing here is that the OH group on phenols is connected to an sp2 hybridized carbon. With alcohols, the OH group is on sp3. And alcohols will not dissociate in water. Okay, and this will also be important later because this is a strong nucleophile. So Okay, so ether synthesis, I think we'll get into this mechanism, I think later this semester too. But for now, you just need to know the reaction. And I'll probably ask you something to the effect of, like what was on the homework. How do I make this ether with an alkoxide and an alpha halide? So basically, what you do with these, you just split them at the ether bond, make 1/2 an alpha halide, 1/2 an alkoxide. No big deal. Simple enough, right? So if you run into these, he asks you to work backwards, gives you a product, and asks for reactants. This is, so in ether you have an alpha group on either side of an oxygen. You'll just split it at the ether and make whatever side's the primary side your alpha halide and the other side an alkoxide. So you just add the negative charge to the oxygen and a metal, and then whatever halogen to. And it doesn't matter which metal, which halogen you use. You can use lithium, you can use chlorine, whatever you want. But you'll end up with the ether and then NABR as a byproduct, or whatever metal or halogen you use. So be prepared to see these.
So you're splitting it right there with the O's every time?
Mm-hmm.
Like you get one R group with the O and then the other R group goes with the.
Mm-hmm. Yeah, because ether synthesis, you're reacting an alkoxide or phenoxide with an alkyl halide, and then you'll form the ether with the oxygen in the middle, this R group on one side, and this R group on the other one. And then these will bond to form your byproduct. Does that make sense?
The A and B are go away, right?
What do you mean?
They're gone, right?
I mean, they're there. They're not
Oh, I
doing
mean, yeah,
anything.
but I can't see them, right? At the end product. No, I don't have to draw them, right?
Technically, you should, yes.
Oh. Okay.
I don't know that
So-
you would count off for that, but
So like if the question was how to make that plus NABR, is like, would he do something like that? Would he
No.
make it that?
No.
No, I was gonna say.
he wouldn't give you that.
I was gonna say that'd be a dick
But we
giveaway.
can use NABR.
Yeah, so he would give you this. He would not tell you that NABR or whatever.
I can't make it that easy.
No, unfortunately. So you'll have to recognize that this is an ether and think about how you make ethers and then go from there.
So is NABR the only one you can use?
No, you can use either sodium, lithium, you can use bromine, chlorine, iodine.
Okay, so the HX.
Yeah, so whatever halogen and whatever alkali metal you can use. All good? I don't know if he'll ask you these. He really didn't do much with ether synthesis.
I was gonna say, I actually asked him a question like after class about this, cause like in the class notes, like, it's, but basically like the sodium disappears, like in the class, like under the mechanism, and I was like, what happens to the sodium? And he didn't really give me a good answer.
So, okay, so for alkoxides or like phenoxides, most of the time you will not see this just because it's an ion, it's not doing anything, it's a spectator ion, if you remember that from Chem 1, probably not. So it's not doing anything in the mechanism. So if something is not participating or doing anything, because I end up with NABR, which is an
That's what he
ionic,
said, yeah,
which
he
is an
literally
ionic
said
compound,
here.
right?
I was like, I don't know what that means.
Yeah, so I start with, I have Na plus here, and I end up with Na plus here. So this is an ionic compound, so this doesn't really, it's not doing anything. Does that make sense?
It doesn't want to react. It just sits there.
Yeah, it doesn't react with anything, it's not gonna affect anything in the mechanism.
I guess I just would get confused because it's like didn't in the homework we had to put like a carboxylic acid and alcohol together to make
So that's,
or an ester?
yeah, that's esters, this is ethers.
Okay.
So be careful there, yes.
I think that's where I'm getting confused.
Yeah, okay, let's back up.
Ester and ether. Oh,
Let's
But
back
that
up.
was just my reason to find a way to
Okay,
explore.
yeah.
that acidification was so, and he was looking around, wrong.
My bad. So this is an ether. So an ether has an oxygen with just some alkyl group on either side. We have no double bonds. That's it. Okay?
So if, when it comes back to the test, and he gives us that, right, he gives us something similar to the psilocybin you just gave us.
Mhm.
On the same side, we can just use NABR.
Yeah.
If we can remember.
That's what I normally default to, but yeah, it's up
Would
to you.
he like make it clear on the test that they like using like ether system, like synthesis?
Probably not.
I'm assuming no.
Yeah,
Okay.
probably not.
Okay.
So it would need to look like that bottom part,
I'm normally up at 10.
not nice, but
I'm normally up.
You would just need to have an oxygen with two alkyl groups on either side.
Okay.
That makes sense?
yeah.
Okay.
And then so would we get it wrong if we put in ABR like with our product? Like the
No.
Yeah.
So, okay. So back to that. All right, hold on. So it's never wrong if you
Yeah.
put
Like I was
it,
just wondering.
That's how the peer educate.
it's never wrong if you put it in the mechanism, but sometimes we just leave it out because it's not of importance to us. Okay, so if you wrote it just like that with NABR as a byproduct, because it is a byproduct, and then included it here, it's not wrong. Sometimes you will see without the sodium because this is ionic, meaning that it's a spectator ion. You cannot do that with the bromine because that's not an ion yet, because it's going from, there's no charge on this to having a charge. So that is doing something in the mechanism. So you cannot leave the bromine out, but you can leave the sodium out. So sometimes you'll just see it with bromine as a byproduct. Does that make sense?
Either way is right.
I'll just memorize NABR.
Okay. Thanks, guy. He's gonna be like, why is everyone using NABR? Okay, are we all right?
Yeah.
Yeah. He just didn't go over this in class. Like,
Yeah, that's what I
I've never
said.
seen this before, I don't think.
Yeah, I don't know if he'll give you this. Really didn't go over this too much.
No.
I thought we went over the mechanism for this, and I know you guys didn't, but I thought when I took it, I thought we did it now. I thought we did the mechanism now, but
I mean, it's in the study guide.
yeah, there's a lot of things in the study guide that are like alkynes will not be on it.
Well,
We
it
didn't do
just
that.
says, like, the reason I asked him was because, like, the study guide says you need to demonstrate an understanding of the reaction mechanism.
Yeah,
and
so we
like-
didn't go over that. So you
He
won't.
didn't go over that class, yeah.
Yeah.
Maybe I'll ask him tomorrow.
Yeah, so I know he will not ask you for the mechanism because we did not go over that. He may or may not ask you for the reaction.
Okay, because that's where I was like making my study guide and like the class notes, like the NABR you just figured under the mechanism in the class notes, and I was like, well, what happened to it? And he said it was a spectator ion, and I was like,
Yeah, so sodium is spectator ion. And then sometimes in general, sometimes we may just leave off byproducts because they're not organic and we don't really care.
okay.
So, I mean, you should have a balanced mechanism, but sometimes they will get left off just because they're byproducts.
So this right here is considered a reaction, or,
Yes.
okay.
So if there's no arrows, no like arrows from electrons to other compounds, this is a reaction arrow that has to be there. But if there's no
Yeah.
mechanism arrows, it's just a reaction.
I was like, this isn't our
So long as
study
you don't
guide.
act for mechanisms, we're right, because you didn't go over this.
But I also noticed. that,
Okay,
Like it says this reaction.
are we all right?
Mhm.
Okay. I'm not gonna spend much time on this. This is a carbonyl compound, you know what it is. You have aldehydes, ketones, carboxylic acids. Do we know what it is?
It's a bold assumption.
Okay.
It's a real bold assumption.
Carbonyl from biology.
Yeah, so carbonyl, you have a carbon double bonded to an oxygen. Okay, so oxygen is electronegative, right? It's more electronegative than carbon. Do we know what electronegative means, by the way?
Hey, you
Yes,
know,
it goes up the period.
Yeah.
Get some more like.
It follows that chart thingy.
Okay.
Just see it on there. See it.
Okay.
Fluoride.
Negative.
Yeah, so electronegative means
That's what it
it, good job. So it means it pulls electrons towards itself. So if you have a bond with something that's very electronegative and something that's not very electronegative, the electronegative one is going to pull all the electrons to itself, which is going to make a polar bond. Okay? Okay. So oxygen is more electronegative than carbon, so it's going to pull those electrons up, which makes this carbon partially positively charged, oxygen is partially negatively charged.
So he would ask, what kind of question would he ask about this?
I don't think he would ask, I don't know that he'd ask like about, I don't know, this is more important to understand that these are weak electrophiles because the carbon holds a partial positive charge. That's more important to understand this. In terms of questions he would ask, there's a part where you need to understand on the study guide, the bonding, and that means like the orbital overlaps that form a carbonyl group. In terms of this, he wouldn't ask you anything about that.
Do you have any questions around it?
No, not off the top of my head.
Is that like an S? One to the S.
Yeah. I don't remember. What is this Greek letter called?
Sigma? No.
No, that's not sigma.
No.
It's almost like half for a K to be.
Yeah, yeah, that's delta, right? I think that's delta. Yeah, that's delta. So this just is used to say partial charge, because this is not a full partial or full positive or negative charge, it's just partial. So this symbol just means partial. Okay, so redox reactions, you will get asked about this. Yes.
My question about these, I would say that I actually set a timer, so I'm not forgetting. Every time I was doing these, I was always losing 2 hydrogens. I always lose 2? Or gain 2? Everyone on the study guide always said -2 or +2. And I was wondering, is it every time I lose 2?
I don't think so.
Okay, so these just throw me off.
I don't, let me think. Maybe?
Okay.
I don't know. I think in the course of these reactions, yes.
So I'm gonna lose. Okay, that's all I need to know right now. If I go Monday
Yeah,
night
I don't
at
know.
6 o'clock, I'm losing 2 or gaining 2.
Okay, so this H in brackets, this means a reducing agent. This O in brackets, oxidizing. Okay. So, oxidation means I'm either gaining an oxygen or losing hydrogen or both. And then reduction, I'm either losing oxygen or gaining hydrogen or both.
I'm always just gaining hydrogen in these problems.
Either hydrogen or oxygen, yes. Okay. So, I have a carboxylic acid. I'm going to reduce it. What am I going to get? Does anyone know? Top of your head?
Yeah. Take away the. No, you add 2. Are we adding 2 right here? No, we're losing 2.
No.
Yeah.
Yeah. You're gaining hydrogen.
Yeah. So I'd
And
add
you
1.
lose an oxygen.
Bring that 1. You losing oxygen?
Loses oxygen or gains hydrogen. Oh.
So do both.
So,
Or.
you can do both. You don't have to do both.
So many rules.
This is
I would take away that H out there on the end, the OH.
Can you make it H2?
It's not just free will. You can take whatever you want. Okay, so this is a carboxylic acid. It reduces to an aldehyde. So I take off the O. It's an aldehyde, right? So aldehyde has a hydrogen on one side.
So is that how we know what it's gonna go to, depending on what it is, and then you just know what it goes to?
Yeah, so you remember like that slide that's like, so like a primary alcohol will oxidize to an aldehyde, which will oxidize to a carboxylic acid.
Yeah.
And the secondary alcohol will oxidize to a ketone.
So I'm not losing two, they're right here, we're only losing one.
Well, you lost an oxygen. Sometimes, I think it's, when you're doing hydrogen, it's 2, I think. I don't know.
It's basically, you have to know what's on that slide, and then that's.
Yeah, I would just know that.
The PowerPoints, these PowerPoints.
Yeah, there's a slide that just shows a primary alcohol oxidizes to an aldehyde, which oxidizes to a carboxylic acid. Secondary just oxidizes to a ketone.
Learn all of this and then study for all.
Yeah, just look at the
What is
or
this?
the PowerPoint.
Christmas.
This is not Christmas.
Okay. So and this is going backwards. So I have a carboxylic acid. I'm reducing it back to an alcohol. Okay. So what did I just say? I have a primary alcohol. I oxidize it. What do I get?
Come on, let's take away 2 hydrogens.
Okay. What would that do? So this is primary.
Oh.
So it won't go to a ketone.
Sounded good.
An aldehyde.
Mm-hmm. Yeah, so it'll go to an aldehyde, just like this one. Okay. So
No, this is
this is
real.
a bad example because I ended up with the same thing. That's my bad.
This is gonna be a roll of the dice right
Okay.
here.
All right. Let me clear this up here.
Took away.
Secondary alcohols can be oxidized to ketones.
You lose 2. You lose 2.
Exactly what, that's what I was telling you.
Okay, so this carbon. Hey. Okay, so this carbon here is this carbon here.
Yeah.
This one is here. This one's here.
Yep.
This oxygen is this oxygen.
Yep.
Okay, this hydrogen is one of these hydrogens here. So I
Okay.
lost 2 hydrogen.
Yeah.
Yeah, there we go. Okay,
That's where it went.
all right. Follow me, and then I have a double. I gain a double bond there, but that's just to keep the carbon with 4 bonds. Okay.
So if I just write oil rig for the answer, it'll make it right.
Yeah.
Yeah.
Oxidation's lost.
Yeah, go ahead and do that. Just write down oil rig.
I love that.
Girlio.
Hopefully it's like a small point instead. I don't know.
This won't be, this,
2 point.
I mean, in terms of all the things that will be tested, he may ask like one or two.
I don't mind that. As long as it's like 1 or 2 points. So.
Yeah, he won't ask very many questions on this. But just study that one side in the PowerPoint, and you should be fine. Okay. I don't know. What is this?
Esterification.
Yes, this is esterification. Because I have.
You take the hydrogen on the right and the OH and you combine them and you get water.
Uh-huh. So I have a carboxylic acid.
You know this?
Okay, I know the reaction, but to do the
Why did I
mechanism,
write acid over there? Why did I do that? That's not an acid.
to know the mechanism, a different story.
I don't know if he'll ask me the mechanism.
If he doesn't, I'm golden.
You're expected to know it on the study guide. I don't know if he'll specifically ask you for it.
Well,
We'll see.
he's gonna get a bunch of gibberish arrows.
Okay.
Very vague.
So when you see you have a carboxylic acid and alcohol in your brain, you should be, oh my gosh, it's esterification. So I'm going to make an ester.
Boom, 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 boom.
Okay, so this OH and a hydrogen is going to combine to make water, and then that carbon is going to connect to that oxygen that's left over.
Okay, that's what we like to see.
Okay, So in ester, you have an oxygen that's connected to an alkyl group, and then on the other side you have a carbon that's double bonded to another oxygen. So this is characteristic of an ester. Okay? So ether, you would not have this double bonded oxygen part. You would just have an alkyl group, alkyl group. Esters, you need to have carbon oxygen double bond connected to another oxygen.
So
Okay.
you need to know the reaction and product, no mechanism?
No, you need to know the mechanism. I don't know if I asked before, but you do. So.
Okay.
Okay, and this has to be catalyzed with acid.
No big deal. No big deal. Just make a bunch of gibberish until it looks like.
Okay. So alcohols are weak nucleophiles, right?
Mhm.
Carboxylic acids are weak electrophiles. Okay. So without a catalyst, these won't do anything. They won't react. So I want to make this carboxylic acid a strong electrophile before it will react with an alcohol, and I'll do that with the acid. Okay. So this oxygen has 2 lone pairs of electrons. I'm going to protonate the carbonyl oxygen. Okay. So when I put a hydrogen on that oxygen, it's going to give it a positive charge. When this oxygen has a positive charge, it's going to pull those electrons from that double bond up to the oxygen, which is going to increase that partial positive charge on the carbon because I'm pulling more electrons away from it. Great. Make sense?
Yes.
Okay, so now this is a strong electrophile. Okay, so now that I have a strong electron, now it can react with a weak nucleophile. So this oxygen has 2 lone pairs of electrons. It's going to attack the carbonyl carbon, but it's going to break this double bond to neutralize that positive charge.
You said the OH or the actual bond?
What do you mean?
Like, what's attacking the carbon, sorry?
The lone pair of electrons on the oxygen.
Oh,
Okay, so I added this whole molecule to this carbon at the oxygen. So I made a carbon-oxygen bond here. This double bond broke and neutralized that positive charge. Then with 2 OH groups and then that whole alcohol molecule on this.
That's where hydrogen.
Yeah, so now this oxygen has positive charge because those 3 bonds. So I want one of those OH groups off, but I don't have a good leaving group right now. But from that alcohol I just added on, that oxygen has an extra hydrogen and it has 1 to spare. So I'm going to have an intramolecular hydrogen transfer and move a hydrogen from that oxygen here to one of those OH groups to make a good leaving group so I can take it off. Following me?
Yeah, that leaves and then that hydrogen leaves the.
Mhm.
what's
Yeah.
double bond,
So I
right?
took this hydrogen, moved it here. Okay, so now I have a good leaving group. So now this water is going to come off, and at the same time, that oxygen has 2 lone pairs of electrons. 1 is going to come down to reform that double bond which is gonna help push off that water and keep that carbon tetravalent. Okay, so I lost water, those lone pair electrons came down, I reformed the double bond. So now that oxygen has an extra bond, has a positive charge, but now that hydrogen can just come off, no problem. I'm gonna form my ester. And this is my catalyst that I used here to reform down here. Make sense? Okay. So I made a list of all the mechanisms you need to know. So these are ones you're going to need to practice. All the other reactions, you'll just need to know the reactions. You just reactants products. But these are the ones you need to know the full-on mechanisms for.
So for the O's, do we need to put those dots? Does it matter because of those dots or not?
Yes, because that's where you're showing. So the arrows go from electrons in the direction of where the electrons are going. So you need to show the electrons to show that that's what's making things happen. That's what's doing the reaction. Does that make sense?
Yeah.
All good?
Can you go back to the mechanism,
Which one?
No, I think it's slide
the
15.
list?
Oh, my bad.
So our nitration, halogenation, they're all similar.
So these are the ones about
I'm not tweaking.
Yeah, so these are the EAS reactions.
Okay, now you're making it cool.
All good, my friends?
Yeah.
Alrighty.
So when it comes down to the alcohol plus the alkali metals and then the Williams after synthesis, usually the products
Mhm. Yes. So,
react.
right, so these, you just need to know the reaction. This, you just need to know the reaction. This, you just need another reaction. And the alkylation, you just need another reaction.
Hey, do you put these on YouTube?
Hmm?
You put these on YouTube?
Mhm.
When you put them on YouTube, can you hear you talk?
Yeah.
So you can guide me along? Because like I like the PowerPoints, but
Mhm.
like when you send them, I can't see like what you drew.
Yeah, because I write it in here. So, yeah. So on YouTube, it's like the whole recording of
Oh yeah.
the study session. I just send out the PowerPoint.
Yeah. All right.
So-
Yeah. It's awesome.
Yeah.
Thank you. You're helpful.
You should start like a channel, like
Mhm.
whatever.
The organic
What's
chemistry
up?
tutor.
Yeah,
He's
like
good.
whatever we were watching.
He got me through Gen Chem and Calc.
He's good at math too, isn't he?
Honestly, I think he's better than Khan Academy.